Hi there, so this video is on section 5.6, L'Hopital's rule. So if you remember from chapter 1 when we were studying limits and we would run into from direct substitution having 0 over 0 or infinity over infinity, those were referred to as indeterminate forms. So 0 over 0 we would run into whenever there was a common factor of x minus whatever x was approaching in the numerator and denominator that then you had to try and eradicate in order to see if the limit actually existed or not. Infinity over infinity would come in whenever you're trying to take the limit as x approaches infinity and you kind of think about direct substitution. And we use end behavior model to help us with evaluating limits as x approaches positive or negative infinity. But remember, when you run into 0 over 0, infinity over infinity, that's referred to as an indeterminate because you don't know if the limit exists, or so the limit might not exist, or the limit could exist, but you have some work to do in order to determine if it does. And in your toolbox at that point, you use different algebraic techniques, so like Fado, Ratcon, LCM over LCM, sledgehammer, right, brute force in order to try and get rid of that common factor that was causing the 0 over 0. Or for limits as x approached positive or negative infinity, we used the end behavior model as our reference for evaluating the limit, which we'll still end up using with this new method for evaluating limits called L'Hopital's rule. But using L'Hopital's rule will just give us kind of simpler end behavior models to reference. So what L'Hopital's rule says is that if you are evaluating a limit as x approaches c of f of x over g of x, and you end up running into 0 over 0 or infinity over infinity, what you can do is think about taking the derivative of the numerator and the derivative of the denominator, and then trying direct substitution again. Now, this is not using quotient rule. This is so looking at your numerator, thinking, okay, well, what differentiation rules do you need in order to differentiate the numerator? And then what differentiation rules do you need to differentiate the denominator? Now, you could run into 0 over 0 or infinity over infinity again, where you could then think about applying L'Hopital's rule again until you are able to see what the limit is through direct substitution or referencing end behavior model, or you can clearly see why the limit fails to exist. Okay, so this is a limit that you guys have actually evaluated. I think this is a limit I had in our chapter 1 notes when we talked about the different strategies that we could use to evaluate limits analytically. So through direct substitution, you would see, and I'm just doing a mental direct substitution, right? You'd run into 0 over 0. So this is one of those cases where now we can try L'Hopital's rule in order to evaluate the limit. So the limit as x approaches 1, applying L'Hopital's rule, I find the derivative of the numerator, which using power rule is 3x squared, and the derivative of the denominator would just be 1. Okay, so then now trying direct substitution, we get 3. The limit is 3. Okay, another rational function. Again, if we thought about using direct substitution, we would run into 0 over 0, so we can think about applying L'Hopital's rule. So the derivative of the numerator, just applying power rule, and then derivative of the denominator would again be 1. So we can now try direct substitution, and that would be 6 times negative 2 plus 5, which is negative 7. And some of these you can try on your own if you want, and like pause the video and then see if we get the same answer. So this is another one. It should be familiar to you. We'd run into 0 over 0. So we can think about taking the limit as x approaches 0. And then thinking about the derivative of the numerator, I have to think chain rule for finding the derivative of the square root of x plus 1. It might be helpful for you to to even think about rewriting that as the quantity x plus 1 to the 1/2 power. So thinking chain rule. derivative of the outside, leave the inside alone, and then times the derivative of the inside. And the derivative of -1 would just be 0. And then looking to the denominator, the derivative of x is just 1. So I know most of you could probably go direct substitution here. I am going to think about rewriting this without the negative exponent though before I do that. And then now I can think about applying direct substitution, and we get 1/2. Okay, so this is limit as x approaches infinity. So before, we would have identified the end behavior model for this rational function, right? The end behavior model is side work, it's our reference. We've been like, okay, x cubed over -x, that's our end behavior model. So the simpler equation that has the same end behavior as the function that we're trying to take the limit as x approaches infinity for. So our end behavior model is -x squared, so that's a parabola that opens down. So we actually know this limit would be equal to -infinity as x approaches infinity. And that's pretty simple, but there are times when applying L'Hopital, like maybe even just to be extra sure, could be helpful. There was a free response on the 2023 exam where you weren't told to use L'Hopital's rule, but you had to use L'Hopital's rule in order to evaluate the limit with what the given information was. Okay, so applying L'Hopital here, though, we would get 3x squared plus 2 over -1. So that's the same as the limit as x approaches infinity of -3x squared minus 2. And that is something you know, basically we're thinking end behavior model of this polynomial now instead of the rational function, right? This would be your end behavior model, which has the same end behavior as -x squared. So we can say this limit is equal to -infinity. So you still have to reference end behavior model sometimes. It's just L'Hopital can make your limit look simpler. Okay, this is another one we would have used end behavior model. You would run into infinity over infinity if you thought about direct substitution, right? You can't really directly substitute in infinity, but if we try L'Hopital, that would end up being, well, actually some of you could probably even see this just thinking end behavior model or not even needing to write that out. But we would get 6x minus 8 over 15x squared plus 8x minus 1. You would still, if you thought about using direct substitution, you'd still get infinity over infinity. So then applying L'Hopital again, you would get 6 over 30x plus 8. And then at this point, you would need to think end behavior model to reference, right? Or just like that entire function, that's just 1 over x, right, transformed. So as x approaches infinity, that would approach 0. Okay, this is one where L'Hopital is definitely helpful for a limit like this. This is a limit where before you had to recognize this special trig limit as x approaches 0 of sine of x over x being 1. And then kind of the different forms of that, and you kind of had to memorize that special limit. But here, if you recognize that you'd run into 0 over 0, applying L'Hopital, so derivative of sine of 6x would be cosine 6x times 6. And then derivative of 4x would be 4. So now using direct substitution, cosine of 0 is 1. So this just ends up being 3/2. This is our last one. I think this is our last one. So again, you can pause it if you want to try it on your own. We'd run into 0 over 0 because cosine of pi over 2 is 0. So trying L'Hopital, derivative of 3 cosine would be -3 sine of x. And derivative of 2x minus pi would be 2. So then using direct substitution, sine of pi over 2 is 1. So this would be negative 3/2. And that's it.